Hi, my name is Akshay Gautam, and in this video we are going to explore the paper Probabilistic Tiny Recursive Models, or PTRM for short, from Alpha Archive. PTRM builds on another paper called Less is More Tiny Recursive Models, or TRM. TRM is interesting because it is very tiny by modern AI standards. It's roughly in the 5 to 7 million parameter range, but it can solve hard structured reasoning problems like Sudoku, maze, or even ArcAGI. The question behind PTRM is, if we already have a trained TRM checkpoint, can we make it solve better at inference time without retraining it? The solution? Instead of following one deterministic recursive path, it runs many noisy recursive paths, decodes many candidate answers, and uses the model's own Q head to choose the best one. Now, this notebook focuses only on Sudoku Extreme dataset, and as far as I know, this is the only code implementation publicly available for this paper. So for convenience, I have uploaded it to my Hugging Face, which is used in this notebook as well, and it is linked at the end. Model weight, helper code, data, everything is available in that Hugging Face note repo, right? Let's go through what's happening here. So let's first understand what's happening. What's the problem? The problem is this puzzle. As a human, I can try to solve this puzzle. I'm not very good at this, by the way, so please forgive me. And I'll obviously do something wrong, and then I'll check, and yeah, it's wrong as expected. Let's see the answer. So it's this. Now, can we make a very small 7 million parameter model solve this puzzle? Let me select the same. It's puzzle 1, so let me select the same puzzle. Puzzle 1. Right, we have the same puzzle now. We'll keep everything as default, and then we'll run the actual PTRM model and see if it can solve it. There we go. So yeah, it solved it. Because it's green, it means it's the correct solution. If any one cell was red, it means that cell is wrong, right? So this is basic of what we are doing. We are basically training a model and doing something at inference time to make it solve puzzles like this. Very small model, very efficient. Now the problem is TRM, the base paper that PTRM builds on, has it can run for many recursive steps, but if the starting route was wrong, it will get stuck on that route, right? And PTRM solves this by using many rollouts. It can be understood as you start with many cars on many on the route, and then randomly change lanes while driving and try to arrive, at least one car will arrive at the right destination, right? That is the gist of it, and that is what has been written here in code. This is basically the whole concept of PTRM explained in code. Very simple to understand, and this is the intuition behind it, as I told. So assume this is the wrong, this red one is the wrong road, and if the car started on this wrong road using TRM, no matter how long we drive, no matter how many turns we take on this wrong route, we will stay on the wrong route and at the end not arrive at the correct destination. And let's say this green is the right route. Now in between, this is the yellow route, right? Let's say we started using PTRM at the wrong route, so the red, we started here, but in between we put some noise, we inserted some noise, and we changed lanes, and any one of those cars arrived at this correct route at the end, this yellow line, right? So this is the concept of PTRM in all of its glory. And to understand it better, why number of cars matter and why number of turns matter and why the amplitude of the noise, which is sigma here by the way, matters, we can use this visual. So k is the number of cars, so if we increase the number of cars, obviously our chances of arriving at the correct destination will increase, right? We can change the number of turns the cars take. Now this can also find us shorter routes or better routes or whatever, and sigma is the amplitude of the noise. So how much noise are we inserting at each turn, right? We can change this to see how much variation we can put in our inference. Q selector is again which of the answers are we selecting as the right answer. This can be better understand when we run the real GPU inference later down the notebook. The maths is pretty simple. We have a normal distribution, we sample a noise from this normal distribution, we apply this noise to the hidden state, that is Z, and to the output, so the candidate Y, and X is our problem, which stays the same. And at the end we use Q, the model's quality score, to find whichever is the best answer, the best Q, right? Now all of this can be understood pretty simply if we just run the whole thing, right? Now if we run 100% of data, it will take a few hours, even with the GPU. So we'll run at like 15% of the data, right? We'll keep let's increase GPU chunk size because we have very high VRAM. Thank you Marimo for providing RTX Pro 6000s. So we'll keep the GPU chunk size high. Let's keep it 96, and let's run the GPU inference, right? When we run it, we will see a dynamic diagram of this intuitive thing happening. We start from here, different cars, they are going towards our our destination. This will update in real time as the model as the inference runs, and at the end we'll see a solution getting printed down below, right? See, this is updating. This might not click at once what is happening in this visual, but if you run it, let's say 2-3 times, it will click immediately, and then the whole concept of this paper will be clear of what is happening, what's being done with the paper here, right? Even with the GPU, I think it will run for a few minutes at least. So let's let it run, and at the end we discuss the limitations of the paper. Now it's not perfect, it's a very small model, it's not at all generic, and things will depend on the checkpoint that was trained using TRM in the first place. It will also depend on how pass K and best Q is selected. Sometimes what happens is pass K accuracy will be higher than best Q. It means that our model has seen better outputs, but it failed to select the best output, right? Oh, here is the output. So see, what is our scores? We have 89% for pass K and 88.9 for best Q. It means our model has seen better scores before, but it selected maybe the second best, I think, right? And it obviously renders a solution, an example solution of what it looks like, other details of the run, and I also discussed some future possible research directions. Now for the conclusion, this whole notebook is obviously built on TRM and PTRM papers, and most of the code was written by GPT 5.5. The visual code, so for the graphs etc., was written by Opus 4.8. The idea was my own, the examples are my own, and I also had to write the GPU inference code because I think there is some library mismatch here. So all of that can be found on my Hugging Face here, and the PTRM paper can be read here, and the TRM paper can be read here. So thanks for watching.